Oh, okay. Okay. So, welcome to the seminar of atmospheric sciences at the Institute of Earth Sciences at the Hebrew University of Jerusalem. Today, we have the honor to introduce Alexander Khain. Alexander came from TSAO, the Central Aerological Observatory in Moscow, immigrated to Israel, and as soon as he immigrated, he joined the Hebrew University in 1991 as a professor, as an associate professor. Now, of course, he's a full professor. And only 1 year after that, in 1992, Mark Pinsky came and he looked for where to be. And as soon as he met with Alexander, there was a click, and they worked together ever since, until very recently, unfortunately, on developing the fundamental of cloud physics. As you all know, Alexander is actually, we can say the father of the Hebrew University spectral beam microphysics, and they went much beyond that and developed the theory of turbulence, aerosol cloud interactions, and many more things that Alexander will now show, and he will now in turn introduce the work of Mark. Thank you, Mark. Thank you, Alexander.
Thank you very much. Thank you very much. Thanks to everyone who is with us now. It is with deep sorrow that I have to announce the passing away of my long-time colleague and the best friend, Professor Mark Pinsky, who is a prominent scientist in the field of cloud physics and radar meteorology. We share the grief of Mark's family that lost devoted husband, father, and grandfather. His wife, Luba, daughters, Masha and Dina, and his son, Mikhail, are with us today. I would like first to say a few words about Mark as a wonderful and very special personality. Mark was born in Moscow in 1952 in a family of intellectuals. It was Soviet Union. Then the education was especially important for developing human values, love of studying and knowledge. His father, Boris Pinsky, was born in a small town in Belarus. As family legend says, he came to Moscow on foot, having no money for the railway ticket. He was admitted to Moscow University and later became a professor of psychology, investigating the problems of children with special needs. Mark's mother, Mira, was born in Odessa. She was an engineer. Mira. Mark's elder sister, Rina, was also a professor of child psychology. Mark graduated from Moscow Telecommunication University in 1975, and the same year he started working at Central Aerological Observatory, which is a large national laboratory in Moscow, where he obtained his PhD in geophysics in 1991. After repatriation to Israel in 1991, and until this time, Mark worked at the Institute of Earth Science of the Hebrew University of Jerusalem and since 2006 as associate professor. Mark was talented in many ways. In addition to interest in mathematics, he played the guitar, had a good voice, and sang very well. He was well read in fiction and philosophy, which we often discussed. I want to share with you several photos that capture moments of Mark's life. Parties.
Where is sound?
Parties at Mark's home. It was always a lot of tasty food made by his wife Luba and Mark singing. Yes, this is a picture of Mark's extended family. It's Mark, Luba, Masha, Dina, and his son Mikhail. Here we see Mark and Luba with younger daughter Dina and son Mikhail. This picture shows Luba, elder daughter Masha, Mark with first granddaughter Maya. And this picture I like very much, Mark with his daughters. Mark observed Jewish traditions. This is the Shabbat prayer.
Can we use this? Press
Okay, thank you. Okay. Now I would like to show some pictures when Mark with senior colleagues. Here is in this picture, Mark with Professor Dinevich. They developed a method for radar analysis of bird migration. In this picture, you can see Mark with Professor Claude Beheng, Professor University of Karlsruhe, very famous in microphysics, and Dr. Axel Seifert. Now he's working in German Meteorological Service. Here on your right, here is a picture that where Mark and Dr. Alexei Korolev are working with the advisor, Professor Ilya Mazin. Yes, here is two pictures that our work. Here is we are working in our office in Hebrew University, and we continued working in different hotels during our trips. Here is the meetings with colleagues and friends in Israel and abroad. It seems to me this picture is from England, where we were with Mark, Dani, his wife Mali, Amir Gevati. Here is Mark with Dinevich. Here Mark in company with Mazin, Professor Kogan, and his wife. Okay, another conference, another meeting. Here is a Mark with Professor Krichak and Professor Von Phillips from Lund University in Sweden. Here's a meeting in Eilat recently. Mark with his friend, Professor Alexander Ryzhkov, National Severe Storm Laboratory, and Dr. Alexei Korolev, Environment Canada. And you see our discussion continued also in waters of Dead Sea during visiting of Professor Behan. Okay, of course, the happy moments we shared with Mark, with Mark's wife Luba and my wife Dina during our joint trips. Okay, now I would like to speak about scientific research of Mark. Mark published more than 100 papers, so it is impossible during one presentation to discuss all results obtained by Mark. Part of these results are published in this book before 2018, but of course now he published additional and other papers. Okay, so I have chosen only 4 topics: effect of turbulence on cloud microphysics, theory of stratocumulus and drizzle formation, ice microphysics and Bergeron-Feldhuisen mechanism, and theory of entrainment and mixing. I tried to discuss these problems short. So first is effects of turbulence on cloud microphysics. These are the publications, you see this list of publications. What is the problem? You can see these measurements of Dr. Bringuer and the measurements of droplet size distributions. And of course, Danny Rosenfeld has a lot of such kind of droplet size distribution. You can see that this size distribution are wide, this wide. And from theoretical theory, we should have very narrow spectra. So this is the theory and this is the observation. So it was necessary to explain why droplet size distributions in real clouds are wide and why rain forms in 15 minutes instead of theory that predicts 100 minutes. So we started working on this topic with Professor Prupacher. If you know this large book of Professor, very known Bible of cloud microphysics, and his Dr. Mitra and his Dr. Wall. Here we are young, working with his Dr. Wall and Sabine Würzel, who were PhD students of Professor Prupacher. Okay, so in non-turbulent flow, you know that droplets fall and collide in vertical. So how turbulent affects droplet tracks and then collisions, of course. And so Mark developed to solve this problem a model of homogeneous isotropic turbulence flow model. You can see this is that velocity field is assumed to be sum of a lot of harmonics with random amplitude, but this field obeys all turbulent laws. and spectra minus 5.6, for example, and all other turbulent laws. And in simulations of droplet motion in this flow, in this turbulent-like flow, we see several interesting results. For example, here you can see track clustering. Here, droplets with sizes with radii 100 microns were put with the same distance between drops, but you see track clustering. So we have all droplets moving within similar trajectories. So actually it is some kind of size sorting between the droplets of different size. Here you can see motion of droplets with radius of 100 microns within a turbulent eddy. And you see that initial position of these drops was different, but all of them leave the vortex in the same place. This is very interesting effect. It's called slink effect, and now it's shown that it also affects turbulent effect collisions. And at last, this third picture shows trajectories of droplets of 10 micron, 30 micron, and 50 micron in this turbulent-like flow. You, of course, understand that this is red. It is the largest drops, it's 50 microns. This green is 30 micron, and blue is 10 micron radius. You can see that it is nothing similar to just vertical fall. So droplets in turbulent flow collide on the different angles. And this is extremely important. And relative velocity in turbulent flow, relative velocity between droplets because of turbulence are larger than difference in fall velocity because of gravity. So it is very important effect was shown here in this picture. You can see that Mark and myself are staying near our first poster dedicated to this problem. Now, the next problem was how to represent turbulent flow and how to calculate collisions. Mark's idea was to separate turbulent flow into elementary volumes, very small volumes with sizes of about 1 millimeter. So it's Kolmogorov microscale. In each such volume, wind shear and Lagrangian accelerations are constant. So to solve, and this allowed us to solve problem of collisions. And so the problem remains to generate randomly turbulent shears and Lagrangian accelerations. And here Mark took PDF of turbulent shear, PDF of Lagrangian acceleration measured for large Reynolds number typical of the atmosphere. And he created generator of such generator of wind shears and accelerations, exactly according to these observations. Then we know in each such elementary volume, wind shear and stresses and accelerations. Now we calculate flux of droplets of one size on drop of another size. You see, this is motions without so-called hydrodynamic interaction. So just relative, we took into account relative velocity without effects of the hydrodynamic interaction. So you can see that droplets that start moving from this surface collide with this target. So the problem was how to calculate now collision efficiency. So we calculated backward in time trajectories of these, say, small drops. So this is the area from that each drop from this area will collide the target when we simulate time forward. But when we took into account effects of interaction, hydrodynamic interaction, what does that mean, hydrodynamic interaction? Each drop, when it falls, it creates field of wind, velocity field in surrounding. So each drop that allows approaches another drop feels this velocity field and try to avoid droplet, avoid collision. So only some fraction of this area, droplets that started only from this area, phi1, will collide this target. So it was possible to calculate and calculated collision efficiency in each such elementary volume. Here is again this illustration of the idea. So this is the target, this is the area, green area, droplets starting with green surface, collide target without hydrodynamic interaction, and only droplets that starting with red area collide target with hydrodynamic interaction. So such simulations have been done with help of Khain. We simulated for a long time such tables of collision efficiency and collision kernel, and we found this size, this distribution. You see PDF of collision efficiency, PDF of collision kernel, and turbulent flow between 15 the droplets 15 and 10 microns. And you see that first of all, in turbulent flow, collision efficiency and collision kernel are random values. And please look that green point is collision efficiency and collision kernel in case of gravity. In case of gravity, standard the values, and how collision in turbulence are larger than in case of gravity. Here we took only averaged values of collision efficiency and collision kernel in turbulent flow, and Mark calculated this table. Actually, you see collisions, collision kernel in turbulent flow, and this is a factor and collisional enhancement factor. say, for example, you see 5, 8, 10, it means that in turbulent flow, collision kernel or collision rate is 10 times stronger than in non-turbulent flow. So these effects we took into account in for solving stochastic collision equation of the stochastic collision equation. This is the you see collision enhancement factor that it's between 2 and 10. Then it is known, it's very interesting phenomena that droplet concentration in turbulent flow is non-homogeneous. So we have clusters of drops with sizes of about 1 or 2 centimeters. And this is also actually equivalent to increasing droplet concentration. So it's also equivalent to increase in collision rate. And using 7 observation from 70 clouds, Mark developed such parameterization formula that takes into account effect of inhomogeneity of droplet concentration. So this is results illustration of turbulent effect on raindrop formation. You can see we took typical size distribution. This is a blue typical size distribution, and started simulate in the non-turbulent case and in the flows with different intensity of turbulence. This is a small stratiform clouds. This is cumulus clouds or stronger. This is the deep convective clouds. And what you can see that in say laminar flow, size distribution will not grow significantly. So we have no rain formation, but this is the rain formation in turbulent flow. This is the raindrops, these areas. So we see that indeed turbulence leads to faster formation of rain and wider droplet size distribution. Here is the simulation with our bin microphysical model. This for maritime, intermediate, and polluted cases. For example, this is, for example, polluted case, rainwater content as a function of time in case of polluted cloud and in case of turbulence, and in case when turbulence is not taken into account, and difference in beginning of rain 18 minutes. So its turbulence accelerate rain formation significantly. Second, so this is the first part what I want to say. And second topic is theory of stratocumulus clouds and drizzle formation. And first, the problem. Look, stratocumulus clouds, depth of stratocumulus clouds is 200 meters. And it is actually impossible to imagine how these 200 meters produce drizzle of size 200 microns. No cumulus clouds, there is no cumulus clouds that produce drizzle at such height, at such distance above cloud base. So what's happening with stratiform clouds? And this problem was solved with help of Mark and my PhD student, Lihi Magaritz. She is here, and I'm very glad about this. Yes. So Mark, to solve this problem, Mark developed so-called Lagrangian Eulerian model, and components are the following. Please look this. So this is the area of the model is covered by 1,000 parcel adjusted. So it's continuous, about 2,000 parcels. And these parcels are moving within a turbulent flow simulated by turbulent-like model like that I showed earlier. And each parcel represents small cloud with very detailed microphysics, And so we have warm microphysics and ice microphysics for this model. And we have unique parameters of this model. For example, time step is 10 power minus 2 seconds to simulate growth of small aerosol particles or haze particles. Yes, microphysical processes are, this is the diffusional growth, equation for supersaturation, collision equations, and so on. We have, Mark has the aerosol inside of droplets, so drops were solutions. Sedimentation is taken into account, as well as mixing is taken into account. So now, okay, we have this very complicated model, and we tested that this model very accurate represent evolution of structure of observed stratocumulus clouds. So why drizzle forms? So the idea was that there are some lucky parcels, so along 2,000 parcels, there is a few parcels that produce drizzle, and then they trigger drizzle for all cloud. So, but how to find these lucky parcels? And here you can see dependence, say liquid water content, and here is the reflectivity. Please look. First, liquid water content grows, and it means that droplet grow by condensation, and reflectivity grows. But then, when liquid water content reach about 1.3 gram per meter cube, we have no growth of liquid water content, but strong growth of rudder reflectivity. What does it mean? It means that collisions start. Collision, because of collisions, mass doesn't change, but reflectivity changes dramatically. So these parcels where we have such growth are lucky parcels. Then we see existence of lucky parcels when we look liquid water content rather efficient, effective radius. And also, as soon as effective radius exceed 12 microns, we see drizzle formation in those parcels. So this is a structure of explanation of results. So you have Leahy and Mark found that there are parcels that are located near sea surface and get a lot of humidity, and humid parcels then ascend within cloud. Then results depend on their track. If they return back, and of course liquid water content grows with height. If they return back, liquid water content doesn't reach maximum, and we have no drizzle formation. And if the parcels spend a few time near cloud top where liquid water content is maximum, also we have not enough time. And also those parcels that spend a lot of time in near cloud top are lucky. And so then Leahy calculated fraction of these parcels, lucky parcel, and you see that it's less than 1% of parcels are lucky. And only this, and so drizzle formation depends on only this a few parcels that produce, that trigger drizzle from entire cloud. Okay, next topic. It's ice microphysics. Mark collaborated with, and we collaborated with Dr. Alexei Korolev in these topics, is the publications. No, first of all, I would like to say that Mark calculated separately collision efficiency between ice crystals, graupel, and water. And it was shown that collisions between ice particles in turbulence, the effects of turbulence on collision of ice particle is stronger than on collisions of water. But of course, it's necessary to study this problem more. But I would like to focus on another very interesting problem. How about physics of stratocumulus clouds, Arctic stratocumulus clouds. Here you see how these clouds look like. And what is very interesting, this is the temperature, -14. And this is a picture measurement. The top of clouds is liquid. Liquid. Crystals, but here the both ice crystals and liquid water, it's near cloud top, where yes, of course there is also, but interesting that these clouds precipitate ice. So ice forms at temperatures warmer, larger than droplets. So how it can be? So we used the same model with Mark introduced ice, as I said, and you can see here a picture that explains physics of this effect. So here is a cross-section of cloud. Here is the brown zones where supersaturation with respect to ice and with respect to water are larger than 0. So there is no Bergeron-Feldhausen mechanism as droplets grow. But this green area is area where supersaturation over ice is larger than 0, but over water is lower than 0. So water evaporates water drops evaporate, but ice grows. And here you can see this picture, this large eddy, and in updraft, we have here in updraft supersaturation over water larger than 0, so droplets are nucleated and grow, and we have a lot of droplets near cloud top. But in downdraft, you see in downdraft, supersaturation over water less than 0, and droplet evaporate. But ice continue growing. This is the ice water content. So it's updraft and downdraft. So ice grows both in updraft and in downdraft. But droplets evaporate. So droplets remain only at upper part of cloud, but cloud precipitate ice. Here is actually so Mark and in this study we supported ideas of Korolev that actually static model can be static model and dynamic model. So what we showed here that such clouds, by the way, can exist for so many hours and even days, and so it's very stable situation that that droplets exist under temperature -14 and do not freeze. So it means that they are all the time they form new drops. So it's because of this dynamical effects, large eddies. Okay, here you can see results of the simulations with different ice crystal concentrations, and ice crystal concentration grows, and you understand that if ice crystal concentration is large, we have significant ice takes water, absorbed water, that drop evaporates and droplet evaporate earlier, and we actually have cloud glaciation. So if concentration of ice crystals is larger than 40 per liter, we should not have we should have actually ice clouds. Yes. Now I would like to describe another topic. It's a theory of entrainment and mixing. What is the problem? Again, this is a problem. It was necessary to explain why we have large drops in clouds, in developing clouds, and fast rain formation. But here, people try to understand the effects of mixing, but not turbulence. Mixing with surrounding. And according to classical theory of mixing, we have two types of mixing, homogeneous and extremely inhomogeneous mixing. Here you can see the structure. This is the adiabatic volume. This is the white is the area of dry air that penetrated to cloud, and then two scenario possible. First scenario, mixing is very fast, so supersaturation start to be homogeneous over all volume, and then all droplets evaporate, partially evaporate. So to the end, we have a lot of small droplets. Another option when mixing is low. If mixing is low, droplets within this volume, this volume evaporate, but other drops are not affected. So to the end, we have a few drops, but large. So this is a classical model that consider first adiabatic, that volume are adiabatic, and only final stages are considered. Mark actually solved the problem, time and spatial dependent evaporation mixing problem. So he considered volume, adiabatic volume, that half of this volume is cloud and half dry air. And then actually equation are solved when mixing takes place and evaporation also takes place. And here you can see size distributions under different rates of mixing. If we have fast mixing, so it's here we have this size distribution. Initial size distribution is monodisperse, red. And in case of we have very low rate of mixing, so-called extremely inhomogeneous mixing, we have white tail, wild tail. So mixing leads to broadening of droplet spectra, and inhomogeneous mixing leads to formation of long tail. And mixing, what is very important, that it was shown that mixing is very long process. So results of a huge amount of observations when people try to understand what kind of mixing we have, they are made during transition periods. Not stationary state is not reached. So it is impossible, according to the observations, to say what kind of mixing we have. But of course, the main question is the classical theory correct at all? Because classical theory considers that volume where mixing takes place is adiabatic. But in cloud edges, we have no adiabatic volumes. We have always influx or outflux from this type. So Mark solved this problem when we have actually mixing at cloud edge. This is a cloud, again the same structure, but now it is not adiabatic volume. We have different actually boundary conditions, and Mark simulated evolution of cloud edge. So we have different, say, this liquid water content, how it changes. This is a interface zone, the relative humidity zone, and effective radius. And what we can see, first of all, that turbulence creates only narrow interface zone, about several tens of meters, not more, maybe 100 meters. And second, yes, it was and conclusions of this. Okay, Mark also calculated velocity of front propagation. So found condition or parameter that determines where mixing will lead to increase volume of cloud or to decrease volume of cloud. It's very interesting effect. But actually conclusion was that turbulence cannot lead to dilution of cloud volume. And what follows from observations that clouds are fully diluted. So adiabatic fraction is 0.4 in the middle, no, in the cloud body, not in cloud core. But so it was necessary to consider other effects of mixing on mixing entrainment on other in addition to another than turbulence, and it was necessary to filter out turbulent motions. So Mark developed method of wavelet filtering techniques and separated, you see here, cross-section of vertical field of vertical velocity, horizontal cross-section of simulation of cumulus clouds with resolution of less simulation with resolution of 10 meters. So you can see here red is updraft, is downdraft, is fully turbulent like picture. But after application of wavelet filtering, we have, this is a convective component of motion, and this is the turbulent component of motion. Sum of these fields and exactly gives us initial total field. And you can see when we see convective field, we can see updraft, strong updraft in the center, and downdraft over the cloud edges. So this is actually structure. It's cross section, and turbulence is random values you can see here. And here actually it is cross section of so-called ring vortices. Actually, it's horizontal cross section of toroidal vortices, and it was shown together with a group of Ilan Koren that namely toroidal vortices play the main role in entrainment and mixing and determine major cloud properties. Okay, I have no time to speak about contribution of Mark to radar meteorology. Here you can see, actually he developed together with Professor Vyshkov so-called polarimetric operator that allows to reproduce or calculate all polarimetric radar reflectivity signatures in terms of microphysical variables. So we look what polarimetric radar or radar shows, and we can send what kind of microphysics we have. And second is the calculation of parameters of cloud turbulence from vertical looking radar with Dr. Krasnov in Delft University. I mentioned already this. And of course, we had with Mark plans for work, for future. And one of, it seems to me, good ideas that cumulus clouds generate gravity waves. Gravity waves move in different directions and create updrafts and downdrafts. And if humidity is large enough, we have formation of secondary clouds, and we have field or cloud ensemble. So one cloud should create cloud ensemble. And with specific wavelengths that determined by gradient of temperature, wavelengths or fraction, no, frequency, sorry. Okay, but it is our plans. So, what I can tell you that despite of so difficult situation, sore situation, we should be thankful for the privilege of knowing Mark, working with him, learning from him, and sharing great moments of comradeship, intellectual richness, and humor. I personally happy that I met Mark in my life and happy that we are able to spend over 30 years working and traveling together. Thank you.
Thank you very much. This touching presentation. Any questions in here? We'll check on the chat. Well, there are 71 participants in the Zoom. This is remarkable. It actually shows the respect of the whole cloud physics community to Mark. So let's see if there. So probably there are people there who want to ask questions. Please write it in the chat. If anyone says something, please go ahead. Yes, please. Can you? Okay, I'll repeat it. Please go ahead.
Are you very close also to the problem of aggregation, or is this relevant to the problem of aggregation now, or is it not?
Please repeat the question before you answer.
I'll repeat the question.
Oh, sorry, I do not hear.
So
Can you?
The box,
Yes.
are these relevant to the problem of aggregation that we see now, or is this just a separate problem?
Actually, no, of course, we can speak separately after this lecture. I suppose that it's possible to do this.
See, the messages, people are thanking very much the interesting talk in memory of Mark. They say that they learn a lot about his interests, especially in turbulence. So again, the whole community is appreciating Mark and your work, your combined work. And thank you very much again.
Thank you.